Good evening, everyone. Welcome to Parikrama, an enlightening journey through the cosmos, hosted by DhruvaAstronomyClub. I'm Shravani, your host for this celestial adventure. Before we dive into the cosmic wonders, let's get acquainted with the force behind today's event, that is Dhruva Astronomy Club. Born out of passion for the stars, this club is dedicated to spreading the knowledge of astronomy to all students regardless of their engineering background. Our aim is to ignite curiosity and foster a love for the mysteries of the universe. Now, let's set the stage for Parikrama. This online workshop is designed to create awareness regarding space and satellites among engineering students. Today, we are honored to have a distinguished speaker who will guide us through the intricacies of space exploration and satellite technology. I'm thrilled to introduce our esteemed speaker, Mr. Supantha Sen, a seasoned scientist at ISRO. Mr. Sen holds a BTech from West Bengal University of Technology, Kolkata, and an MTech from IISc in Electronic Engineering. His journey includes being an ex-analog engineer at Analog Devices, bringing a wealth of experience and knowledge to our event. Without further ado, let's welcome Mr. Supantha Sen to share his insights and expertise. Mr. Sen, this virtual stage is yours now.
Thank you very much for introducing. And I am grateful to this Dhruva Astronomy Club for giving me this opportunity to share some of the details of the satellite technology and space technology. I will go through, it will be a little informal kind of thing, not a formal. So you can just stop me anytime and ask any questions if you want. And I'll be presenting some slides, but these are not that much slide-like thing. It will be some images only, and I will share some of the details that I am aware of and I am working. So is my slide visible?
Yes, sir.
Okay, fine.
Yes.
So I'll be starting. So actually, when it comes to satellite, so there are three questions that in mind, like what is a satellite, where is a satellite, and how a satellite works, or what is the physics behind satellite, or what is it. So uh, can anybody from you tell what is a satellite? Any like raw answer only? Can anybody tell?
Object that is sent out in space to observe either the cosmos or the Earth.
Okay, but you are more detailed. Satellite, like by definition, it is any object that is moving around a celestial body. Like, yeah, moon is also satellite, so it is not that it has to observe something or not. It can be any object. like so this artificial satellites are the, like that, it can be natural or artificial. So natural satellites are any moon of the planet, or the, like, our planet is also a satellite of our star, you can say like that. So but the thing is, in when we make some artificial satellites, it will be used for some purpose. So there it comes, this observation or whatever the role of the satellite that will come. So this is the definition of satellite. So it may or may not be in space also. That is not a constraint that it should be at space. So generally, like, it is defined that over 100 kilometer of our Earth surface, it is considered as free space. But if some object is rotating, like, rotating means like it shouldn't be like a flight, like something is going from one place to another. That is not a satellite, because the satellite has to move by the like, not flown, or it should be a natural two body system. So that I will go through a little detail. So next is, where is the satellite? So, like, where is the satellite, and this what, So generally speaking, why a satellite needed and where should we put it? Like this where question will be answered by why we need a satellite. So I will tell you a small like analogy. Like we generally speak like God is watching us from above the sky. So generally, why we speak of this sentence, like why uh, God is seeing from above the sky, not below. So the physics behind is it the field of view. So if you are at a higher altitude or something, you can view a large region altogether at the same time. So that is the main reason why the satellites are placed above the sky or in the space so that it can cover a wide uh, region, like the whole of India it can cover at a single go or something. So that depends on now at which height you will put, that depends on the application. So if like you have put into some 700-800 kilometers height, you will not be able to see full India, or depending on the like uh, application you can put it, like some geostationary satellite will be there that I will go through in little bit more detail. So that will be used for communication and that should be visible all over the India at the same time, like any place in India can view the satellite. So that they are put in very high altitude, like 36,000 kilometer or something. So this is where, and now next is how. How means how you will put the satellite, how it will work, and what it will work. Those will be coming in this how of a satellite. So the next thing is, so this as I told, orbits like satellite, as I told, it's any object that is moving around a planet or something, or any other celestial object. So it has to move into some orbit, and this orbit who will decide? Orbit we like say moon is revolving around the earth. So that orbit it is natural orbit. So we are not defining it. But when we are launching a satellite for our purpose, we can define the orbit. So based on that orbit, our satellite will be there in the space. So it also depends on what is the function, like what is the function of the satellite. So as you can see, this based on the shape of the orbit. Like you all are engineers, so I can tell this this famous conic section. So based on the conic sections, this orbits can be defined. So this circular orbit is there, elliptical orbit is there. Mostly all of the satellites, like natural satellites, are in elliptical orbit because, as you know, or from the plus 2 level, that this Kepler's laws of planets are there. So it's any two body problem. So to like any satellite or any object moves in an elliptical path with the like with the center object as one of it focus. So this is an elliptical orbit, and if that elliptical orbit is modified, then we will get a circular orbit also. Now next is parabolic and hyperbolic orbit. So this, as from the image you can see, these orbits are like you are not revolving, like you are escaping that sphere of influence of that center object. So when we are when like you have to send some object, or say you are sending a rocket to moon, then from the earth sphere of influence you have to go out. So then you will use this hyperbolic or parabolic orbit, depending on the, like there is a small difference between those two, that depending on the velocity or whatever it is needed, you have to put that satellite or that vehicle or spacecraft into that orbit. You can't put in elliptical orbit and then launch, like it will not go to moon, or it will not leave the earth. So this is what based on the shape and based on the inclination also it is defined. So as you can see this bottom image, like there are three inclinations, like one is along the equator, one is along the pole, and one is inclined. Like inclined can be any degree, from 0 degree to 90 degree, any degree it can be. So how you will select it, that I will tell you. Based on the applications you have to select. Now again, this based on altitude also it is defined. So as I told, if you want to view the whole of like a satellite has to view the whole of India, or like a whole very big region, and every place should have the visibility of the satellite, then it should be put in geo. So geo, that orbit altitude is 35,700, so around 36,000 kilometer. And LEO and MEO are also there mostly. So satellites basically we can classify it as like mostly will classify as like one is remote sensing satellite, one is communication satellite, and some are navigation satellites, and others are like this astronomical, or that is for viewing some cosmic source or anything like that is viewing the outer space or something. So this remote sensing satellites, like when I'm coming to the application, so as I told, the basic concept of satellite, artificial satellite, is we have to view a big region from the sky. So this like remote sensing satellite is like when you are seeing this Google map or something. So what you are seeing the map of the whole city. So this whole city or whole India, this map is coming from satellite image. So that image is taken by a class of satellite called remote sensing satellite. And this mapping is just a trailer. You can say the trailer like is a small part. Remote sensing satellite also covers like some natural resources. Say you have to monitor this Amazon rainforest, how much like deforestation happened or whatever, or say you have to monitor this ice glaciers, or any other polar regions you have to monitor, anything you have to monitor, and any remote sensing you have to do. Remote sensing means like remotely you are getting information of the object that is far away from you. You are not touching it, you are getting the information. So that is remote sensing. So any remote sensing covers a vast gamut of things, like anything can be remote sensing. You are finding the temperature of the say Himalayan regions, that is also remote sensing. So these kind of satellites are like this your remote sensing satellites. So mostly we'll put remote sensing satellites in LEO orbit. There are some constraints why we'll put in LEO orbit, not in GEO. We some satellites like NASA also have tried, ISRO also have tried, or some others global space organizations also have tried. But the thing is, uh, yeah, in Geo, from Geo some constraint is there, like you will not get the resolution of the image that you are getting from LEO. So we will put remote sensing satellite in LEO around 600-700 kilometer height. So that depends on the applications again. And MEO satellites are used mostly for communication purposes. So and defense purpose also it will be used. In LEO satellites now also we are using it for communication, like this Starlink you are aware. They are putting this uh, internet services from LEO. So in LEO, as the height is less, you have to put more satellite to cover a single region. And GEO satellites are mostly communication satellite, like TV broadcast or whatever. So because in broadcasting systems, what you need is you need 24/7 view of the satellite. So this is how these orbits are defined. Now I will go to another kind of orbit, is Aditya L1. As you all know, this Aditya L1 is this is in a halo orbit, not like the orbit that I have told you. Because say generally when I am putting a satellite, it's a two body problem, as you say, because Earth is there and the satellite is there. So your physics will lie on the gravitational forces of these two objects. But this Aditya, it was put in a halo orbit, and halo orbit is like it's for a three body problem. So you have to observe the sun. That's why Aditya is launched, as you all know. So you have to observe a sun, and you can't orbit the sun, because the making orbit around the sun, it is very difficult because it has to travel very large distance. So that is not feasible. And if you revolve around the sun, it will take a long time to reach, like to encircle the sun. So that is not a feasible option. So what you will do, you will consider it's like your satellite will not be in the influence of Earth, uh, or you can say it won't be orbiting Earth, or it won't be orbiting the sun also. So you will put in a place where both the forces are balanced. So it's a halo orbit. As you can see, this L1 point, this is actually an imaginary point. So around this imaginary point, this satellite is revolving. So this orbit is a little bit different. So that's why I wanted to mention it. So next is, say this is generally remote sensing, what I was telling. So see, if you are putting a satellite in LEO orbit and a polar, like as I told, based on shape, based on inclination, and then based on this height. So Leo and then polar. So if you put the satellite, it will move from north pole to south pole or south pole to north pole, like that. So that right image I am showing, it will cover the globe like this. So you can take the image of the earth surface in different locations. So this left side is just a depiction of some temperature or something of the globe. So this kind of scanning can be done by satellites also. So next is, now I will come to how. So uh, this image you can see a satellite seeing the earth. So like many people are aware or not aware, like this satellite, people, like by seeing it, what can you guess? Like it's a box and one panel is there above and one rod is there in the right. But uh, to know everything, like it is not that it's just a structure or something. Everything has a purpose of it, like why it is there. So I will get into little detail of the subsystems of how these satellites are made, because these basic concepts are needed first, and then only you can build a satellite or build or think of a satellite that can suit your purpose, what you need. So in this satellite, like that last image, as you as you see now, this image, like some definitions are there. Like satellite, generally you are sending it to space, so you have a communication link between your satellite, but you are not there at the satellite. So if something goes wrong, uh, then you can't go and repair it. So you have to make the systems very reliable, and I will get into some more details of how you will make it reliable and all those things. So this image, from this image you can see, like you have a this science instrument one, that bottom it is written. So it will be the science instrument, means it is the instrument that will that is for observing. So observing means it can be a camera, it can be a radar, it can be a like it can be a like this uh, whatever, any kind of sensor, thermal sensor or anything. Then your sole purpose is to put the science instrument so that it can view from above the sky, or it can view a long like a big region. So next is how that data will come to you. So here comes this communication device. So you have to put a processor there, you have to put an antenna there, you have to make a this RF front end, what we call, like it is the like your data had to be modulated. If there is some electronic students between you, they will be knowing. So you have to modulate the signal and then you have to send, because you can't just send the signal directly, because it will, there will be noise and all, like it can't travel this much long distance without modulation. So modulation is just like a carrier. Like when you send a letter to somewhere, I am explaining this because like non-electronics or non-electrical students are also there. So if you are sending one letter to say from this Bangalore to say Delhi, you are sending. So you can't just throw the letter. That some postman has to carry it, and then this postal service has to deliver the letter. But finally, what that destination will get is the message that is written in the letter. And what I am sending that message only. Other things are taken care by the postal service or whoever is there. So this is called modulation. So modulation is basically like you have the data signal, but it is embedded, or you can say it is like it is modulated basically. So it will be translated into some other frequency or some other kind of signals, and then that signal will be transmitted, and then it has to be further demodulated and to get the like data signal. Now here further things comes, like you can modulate and demodulate. These are general schemes, so anybody can uh, get your signal. So if you have some secret information or something you want to share, then in addition to modulation, what you have to do is encrypt. So encryption means you will change your message based on a key. Like you will have a key, like say if I define like A B C D, we all know. But say if I define A will be like we'll start from opposite. So A will be Z and B will be Y, like that. So that is my key, that I am starting from the opposite side. So this is called encryption. So every satellite will have some key, and that key, who is the like manufacturer of the satellite or who is operating the satellite, they will know. So if satellite is sending some signal, they can easily able to decrypt the signal and get the actual data what is needed. And the third thing is like below communication device. No, so this communication device further comes complications comes like what antenna to be put. Like actually the thing is when you are transmitting this long, say 800 kilometers, 900 kilometers, you actually need a very big antenna to pump that energy. But in satellite you won't get this much big space to put the antenna. Even if you in the satellite, if you get, you can't launch the satellite, because while launching many things comes into play like the weight of the satellite or whatever. So so that there comes a challenge, like you have to make a small antenna, but it has to pump that much energy. So the antenna, some like very engineering marvelous antenna designs are there for the satellite. It is different from what in ground antenna we are seeing. So the third thing is this container, because your electronics whatever you are putting there, like say your camera data will come, then there will be processor, then that modulator, demodulator, whatever it is, all things you have to be put into a container. Why container? You can because like space, it is vulnerable to many issues, like you are vulnerable to some electrostatic discharge, some charge can come, and you are vulnerable to radiations, you are vulnerable to this cosmic rays, or many things are there that can burn your system. So that's why you need a container. And also temperature control is one major concern in satellite. I will come into it. So third is this power source satellite. So power, where you will need power, so one to drive this electronics, so electrical power you need. And say you are in an orbit, but you like with time that orbit, you will degrade the orbit. Like say consider you there is a point between like two objects, and two objects are like giving equal force, and that middle point is balanced there. Say 1 meter from 1 meter from this one body, and 1 meter from the other body, like two that is balanced properly. But it won't, like say it will be balanced when we are considering that it is exactly at that point. Say it shifted by 1 centimeter here and there, then slowly what will happen is one side force will dominate, and other side force will lose. So slowly the object will move because of the unbalanced nature. So the satellite, when it is in the orbit, many things can happen. Say some asteroid hit, or some due to some solar radiation, or some due to anything. If there is a small shift uh, in the like satellite path, then it will deviate. So you will need some energy, or some thrust, or you can say some, like you have to add some engines in it to bring it back to the desired orbit where it should be. So that power is generated from like you will put some fuel in the satellite, like that fuel thing I will come little bit, that is really complex things. Because so the solar panel, as you all know, here in the earth, when you are putting a solar panel, you are putting it oriented to the sun, uh, and you are getting the energy. But satellite will revolve, so it will not be oriented always towards the sun. So we have to have a mechanism to orient the this solar panel. So if you see the earlier satellites, like first satellite what is being made by any global organization, they will put the solar panel on the container itself in a circular fashion, so that anywhere if it is oriented, then you will get the sunlight. But actually you are losing some losing efficiency on that, because that time we don't have this like deployment mechanism, like how this solar panel will be deployed and then oriented. So that's why they were put it like this. Now we have all these complex servo mechanisms to deploy the panels, and then like orient it towards the sun to get the thing to get the required power. Now, as I told, temperature, in Earth, when you are at the sun, so you will feel hot. Okay, so when the like solar panel or something like uh, in Earth, when you are putting, it will be hot, and the night time it will be cold. But how much is the temperature difference? Say hot means say 30 degrees Celsius, it will be in the like normal time I'm speaking, and in the night it will be say 29 like sorry 30, then say 25 or something, 5-degree difference, maximum 10-degree difference, or maximum 20-degree difference can be there in the earth's surface between day and night. But in the space where you don't have any atmosphere, it's completely vacuum, so the difference in temperature will be 100 or 200. Like say when you are at the sun, you are at 500 degrees Celsius. Like when the solar panel is pointing towards the sun, you are at 300 500 degrees Celsius, and when it is not pointed towards the sun, it is say minus 200 degrees Celsius. Then this kind of temperature variation you have to take care in the solar panels, in the container, and everything. So here the engineering challenge will come. So that's why I told it, this is an engineering marvel. And like this satellite is not a or not only electronics, not only computer science or mechanical, it is a like multidisciplinary topic. I will come slowly to this like how it is a multidisciplinary, because this choice of materials is also needed. You need engines also, you need electronics also, you need computer science also to process the data and all those things. So this is some little bit more details of the components of the satellite. uh, Now generally we call satellite as mhm, is a collection of all these things. Now first one comes payload. Payload is what I told in the last slide, is science instrument. So payload means what the satellite is intended to do. Say for communication satellite, payload will be a like receiver or transmitter, or say transponder. So what it will do in communication satellite, that I will go a little bit detail in later, but communication satellite that will take the signal and retransmit it or whatever. So that your payload is just receiving, then some processing, and then transmitting. For remote sensing satellite, payload can be a camera, payload can be a radar, payload can be a like thermal sensor, or any kind of sensor payload can be. So based on your need, this payload will change, and satellite is the whole structure. So here you can see, so what are the major subsystems. So in satellite mainly one payload is needed. Payload will be there, one power system will be there comprising of the solar panel and other things, one propulsion system will be there to maintain the orbit. Now this propulsion system I will come to little detail. Third is one is AOCS, it is called attitude uh, attitude and orbit control systems. So this attitude means one is orbit that can be controlled by your this propulsion systems. But how will you know your orbit has changed? So for that some procedures are needed. So that comes under this AOCS. And attitude means say your orientation of the satellite. Say your camera is pointing towards the earth. Now your camera is pointing towards say outer space or towards some other thing. So then you will not get the image of the earth that you needed. So for that you will need the correct attitude of the satellite. So how will you get the attitude of the satellite, and how will you get this uh, orbit of the satellite? So for this some sensors are there, some specific sensors, like one is it is called star sensor, one is called one inertial sensor is there, that is called gyroscope. So gyroscope you may have studied in your plus 2. It is like it will maintain the orientation of a body based on the angular momentum. So that is a mechanical gyroscope. Now electronic gyroscope is also there, some ring laser gyroscope is also there. Like it will based on the optical length, like one laser source is pointed, and based on the laser source you can check the angular momentum of the like actual orientation of the satellite. So those comes in AOCS. And then comes um, orbit control. Now one is called star sensor. So what is the star sensor? Like your satellite will have some sensors that will point towards some stars. Like as you know, this earlier days how we used to navigate. We used to navigate based on this seeing the stars. So actually some constellation or some stars are there, those positions are constant. So those are detected by that star sensors to orient the satellite properly. Because when you are at the space, you don't know which is north, which is south, or what is what. From Earth you can say, because you have a reference system, but there you won't have a reference, because Earth won't be your reference, because Earth is also rotating, or like in its own axis, and it is changing. So this is that power system, as I told. Now these power systems will have many other complexities inside it, because say some charge particle uh, mm, like hit the satellite, and that created a static charge in the satellite body, then your whatever the electronics will burn. So how will you stop it? So and the satellite don't have a ground also, because you don't have a earth. Like generally electrical or electronic students will know, like whatever happens you will have a earthing uh, to save any object, but here you don't have. So how will you do it? So this very vast engineering skills are required for it, to get it. Um so this is the basic subsystems of satellites. If you have any questions later, I will go through any specific systems that you wanted. So I will go next. These are the subsystems, as I told. This is some satellite of NASA. I took the image, just it's a open source image only. Like so, this you can see the top right. It is that star trackers that I told, star sensors. So one thing I wanted to say here, this propulsion, as I told, you need very good chemical engineering skill also to design this propulsion fuel. Now there are 2 3 options. Like say when you are at Earth, when you are uh, using, say, your car you are using, how you are uh, moving the car. Like you are using an engine, or a, like now electric vehicles are coming, so you are using a motor. In motor won't work in satellite, because you don't have any reference, like you are in space only. So uh, let's come to engines. Then you have to use an engine. So engine, what you will use. So generally in our this car, what kind of engines we use? Generally we'll use petrol or diesel that will burn, or combustion will happen, and that will provide give you the energy. So during combustion, here you need air. So generally, if any mechanical students are there or someone, they will be able to understand. Not only they, like they will be knowing, but others should also understand. Like generally, these engines are called internal combustion engines. Previously, we used steam engines that also needed air or water, and then for combustion you will need air only. That those are external combustion engines. And this aeroplane, what they will use, aeroplane will use a gas turbine engine. So those, what it will do, it will take the air and that it will compress it, and then like a turbine will rotate, and it will produce a jet out of it, and then it will thrust your flight or something. Now when it comes to space, none of it will work, because you don't have air. So what you have to use? So generally what is used is, they will use one fuel and another oxidizer. So that oxidizer will have oxygen ions, or generally what is the definition of oxidizer is like that only. So when these two will be mixed, combustion will happen. So now the types of engine comes from uh, in what state this fuel or oxidizer is. So if both are solid, then it's a solid engine. But now generally, if you think a little bit, like satellite, when you are putting into some orbit and you are correcting the orbit, you need the thrust. You have to give a precise thrust so that it won't go the other way. So how will you give? If you have a solid fuel or solid oxidizer, or this is called solid engines. solid fueled engine. So solid engines, if you use, then you can't control it, because you don't have the freedom of controlling it. So, because once you light it, the entire solid will burn. Takes the rate you can't control, and you can't stop it in between, because you don't have anything to stop it. So another thing comes this liquid engines. So I think you have all heard about cryo engines and all those things. Cryo, like everything comes under liquid engine only. Just the temperature will change. Like it will be in around 0 Kelvin. That is called cryo temperature. So I will generally tell it is a liquid engine. In liquid engine, you can control it very easily. You will, if you have a liquid fuel and a liquid oxidizer, you combine it, like whatever however amount of thrust you need, you combine it, and then you will be easily able to control the thrust and get it into orbit. So for that you need that fuel to be stored. Okay, I am telling solid, liquid and gaseous only. Like solid, liquid and gas I am not telling. Why? Because when you since you have a space crunch, like you need to have very store it in a very tight space. So when you compress the gas, it will become liquid only. So that's why I told two classes, liquid and solid. So that space you required, even if fully compressed, that tank you have to put somewhere in the satellite. So today most of the space in the satellite is taken by this propellant only, and the life of the satellite also depends on the on how much propellant is there. Because once, say after once you have launched a satellite after 10 years, your propellant will finish slowly, how many ever orbit maintenance you have done. So once you are out of fuel, you can't maintain the orbit, so you are gone. So that is the main one major challenge. Electronics won't go bad in this much time, or you can make this better, but you're keeping the fuel is the major challenge. So people have started now many things, like they are refueling the satellite also. Uh, some agencies, I'm not sure, but they are taking up this challenge, like they will send some rocket to the satellite again, that will refuel and then come back. So but that is a bigger challenge. So so this life of the satellite. Now another solution what we have got, like it's in cutting edge technology, you can say electric propulsion. Because you have abundant electrical power in your satellite, because you don't have cloud there, you have nothing. Solar panel, if you orient properly, always you will get sunlight, and you can generate whatever power you want. Okay, based on the size of the panel. So if that electrical energy somehow it can be used as propulsion, as I told, motor is not there, so it is out of question. But people have used, like people what that the thrusters, they will bombard some ions, uh, and that like from Newton's third law, that you can say that some reaction will come, that reaction will move the satellite. So people are trying it. This is the cutting edge of technology in now time. But it has some other issues also, that I am not discussing here, but some more very major issues are there. That's why it is not came into picture till now, like full fledged it has not came. Some technology demonstrators or some things have came. Next, now this remote sensing, I will come slowly. So as you can see, remote sensing. So if you know the spectrum, so I have that this spectrum. So if you know the EM spectrum, then you know you have radio waves, this infrared, then this visible, and then again this like high frequency waves are coming, like your X-rays, gamma rays, and high energy waves. So visible part is just a small part of it. You all know, because you all are engineers here. So visible is very small. There is many things outside the visible region. So this remote sensing can be done in any region you want. So generally for Earth remote sensing, that is called Earth observation, we'll use visible region, we'll use infrared region, and we'll use microwave or radio waves. This complete region we'll use. So visible region means you need a camera. So the two like the physics is little bit different, because visible region means your sun is striking some object and that reflection of the sun rays are coming. Your eye is seeing like that only, like sun or some light source is like irradiating some surface, and the reflection from the surface is coming to your eye and you are seeing it. So this is called reflection, like some source based, like reflection based. So this is called reflection. Second is infrared. It is one region, some uh, you can see here, like some lower frequency than this visible. So there what happens, there reflection happens, that is fine, but a major contribution is their emission. So you all have read in your first year, or you have read in your plus 2, some black body radiation is there, Planck's law is there. So I am not going in detail. So what it will do, what like generally, if a body has some temperature, it will emit by its own, no source is required. So that emission, whatever you are getting, black body will radiate, like will emit the most, and other body will emit based on that, compared with the black body, what is the emission. So that is called emissivity. So based on the surface it will change. So that emission, that thing you can capture. So those are called thermal sensors. So in visible you have camera, in infrared you have thermal, and microwave again it will come when further low frequency, like say left side is lower frequency and wavelength is higher. So if you want, you little bit you study electronics and electrical students will be knowing this, not only that, everybody will be knowing, here left side is frequency is low, so wavelength is higher, and if wavelength is higher, your scattering is lower. Why? Because the phenomena of scattering, like Rayleigh scattering or many other kind of scattering are there, that depends on the wavelength. So if you have very high wavelength, your scattering is very less. So if you remember one famous question, like uh, can anybody answer this, like if you are hearing till now, I have bored you or not, I don't know, like why your traffic lights are red, like to stop you will use red light only. Why? Anybody?
It travels the furthest distance without scattering.
Correct. Why it travels a further distance? Because its wavelength is the highest. Okay. So if you go further, this microwave region, it will be further higher, and it can penetrate even clouds and everything. So if you have a radar sensor in it, it will penetrate the clouds also. And in rainy season also, you will be able to see. Like visible, if you have put a camera in your satellite, in cloudy day it can't see the ground. So that is loss of, like if you take an image, that is really a waste image, no use. But this microwave satellites, like these are radars only basically. Why radars, I will tell. This will use this can penetrate clouds, and in rainy days also you can get the ground information. So now this here reflection is also possible, but you don't have a like microwave source, like very big microwave source is not there, like in nearby us, so reflections are little bit less. So that power is very feeble what we get from reflection. So what we do, we'll use a we will use an active sensor, like we'll pump our own energy. Like your satellite will send energy in microwave region, and that energy, when it reflected from the surface, it will come back, and you are like sensing it again. So so you are getting the information finally. So you are generating your own source. So this is called, this is the three broad classes, like microwave, visible, and infrared, of remote sensing for Earth. Now this some other sensors are also there, like X-ray sensors and something. Those are used for these astronomical objects. As this recently we have launched this ExpoSat, so it is in that X-ray region. So X-ray and polarization I will come later. Expo is polarization. So so this is the basic satellite. So I will tell this remote sensing in a little bit more detail, because very complex mechanisms are there. So you have an energy source, that object of study, your reflection, emission, whatever you are studying, you are getting it in this into the satellite. Now this satellite sensor, you have to transfer the data to ground, and then you have to process it. So here, as I told, multidisciplinary, here many things will are coming. So physics is coming, electronics is coming, for satellite mechanical is also coming, this ground station you have to put the antenna, that antenna should track your satellite. So civil is also coming. And again this for processing some electronics, computer science, servers, everything is coming. So after that, anybody has any question? Okay.
No, sir.
Okay, fine. Then now I will tell you what is that optical sensors. So you have many kinds of resolution to define your sensors. So in optical I will tell, one is this radiometric resolution. Radiometric resolution means if you have a data, like say a camera data, when you are using your mobile phones or something, when you are putting that camera, so you are getting a image. That image is generally RGB or CYMK. If anybody has read or something, they will know, but I will tell. This your image, that will be a combination of some red band, uh, blue band, uh, uh, blue band and green band. So RGB and CYMK. This cyan, some another brand is there. Uh, or that is 4 band, so 3 band or 4 band. But in satellite image, we use multiple bands, like 13 bands also we are using. So that now what comes is radiometric resolution. Like if anybody has done some soft, like analysis on image in phone, when you are capturing an image, that RGB, that three values, based on the three intensity of the three values, your colors are generated. Okay, so if R is higher, like if RGB, I am telling R is high, other two are low, then you will get mostly red area. So each pixel will have some RGB, so three values. So and generally what we use in our phones or something is like say 250 till 256 it will come. Okay, so 256 means 2 to the power something. So that resolution is called radiometric resolution. So that like 0 to 255 I can put that resolution, I can put 0 to 255 in phone what you are putting. That I can use 0 to 1 1024 also. 1024 means 2 to the power 10, so 10 bit, that also I can use. So what advantage you will get? You will get more continuous colors or more continuous information from the image. That generally your eye is an analog system, so it is continuous. But when you are taking a digital image, so it depends on the this bit resolution or radiometric resolution. Based on that, your intensity or your quantification, like each intensity of light you can quantify into say 4 bits, 2 bits, 4 bits, or say 8 bit. So generally we will use 8 bit to 56. But in satellites we have to use more, because we, as the need arises, we have to use more information. 12 bits, even 16 bits also we people are using now. So this is now difference you can see. The 2-bit image you are seeing some cartoonish kind of image, but this 4-bit is little bit more clarity is there. 8-bit some features also you can easily see. Okay, this ground, say this roads also you are easily able to see. The difference you can see. So that I wanted to mention. So now another thing is, this is called radiometric, and now it will come spatial resolution. Spatial resolution means same uh, each pixel in your, like resolution, like higher the resolution, spatial resolution, more megapixels will be there in camera, general terms what you tell. So more megapixels means each, say uh, say you are taking an image of a region, or image of a person, or image of a wall or something. So say 1 millimeter by 1 millimeter, you are getting 1 pixel. Okay, so if you are at the same distance, if you change the distance, that resolution, like that pixel size will change. So but if you are at the same distance and you are using uh, say some x megapixel phone, now if you take x plus something, some more megapixel phone, then what will happen is that same 1 millimeter by 1 millimeter will be given by more than a pixel. So generally, if say how to like I will explain in a better way. This, like people don't think this, but say if you have a line, small line, 1 millimeter line. but your pixel size is more than 1 millimeter. So each pixel will have, as I told, will have three values. So RGB, or depending on the number of bands, number of values. So uh, each pixel you are quantifying with some average value. So you won't be able to see the line. You will see a single color in that full square area. But if you use higher resolution, then if one pixel is falling on the line, one pixel is falling outside the line, that you will be able to resolve that. So that is called spatial resolution. So in this slide you can see this coarse resolution global, this 110 kilometer maximum. This resolution means one pixel of that image is 110 kilometer in the ground, like 110 by 110, like that. So that means in 110 kilometer, whatever is there, you will everything will see as a single value. So that is helpful when you have a homogeneous area like ocean. You have to do ocean means kilometers by kilometers, it is same only. You don't need that information. So you will use lower resolution satellites there, then continental, then this national, regional, then when your Google Maps, when they are giving, so what resolution they are giving, if you see below, like generally if you see below, it will be written some 2 meter or 3 meter resolution it will get. So you are able to see the streets in the Google Map. But if your resolution is further higher, say 1 centimeter resolution, you would have been able to see humans also. uh, so that is what this spatial resolution is. Now next is, see, this is that spatial resolution. This left side image is 30 meter per pixel. So each pixel is 30 meter on the ground. If the rightmost is 300 meter. So see, you can see the difference. You are able to resolve finely these buildings and roads in this 30 meter, but that you are unable to do in this 300 meter or 100 meter, because each pixel you are getting that average of the value. So I hope you understood. If you have any doubt, you tell, because this need a little bit of imagination to understand it. Now third is spectral. As I told, um, I have told RGB. Now if you take more VIB, GYOR, all the bands you take, you will get more resolution in spectrally. Okay. Now why it is needed? Because spectral signature, I will show in your next slide or some slide. Spectral signature of different objects are different. Like water, what is the spectral signature, won't match with the spectral signature of this land. Or say vegetation is there, vegetation means some trees are there, you will get green more, and green more is there. But along with green, due to that chlorophyll content, you are getting green in the leaves. But they will emit more in this infrared region also. So if you have infrared sensor, you will be able to easily spot out this vegetation from there also. So that depends on the spectral signature. So this signatures means, what is mean by signature is, it is everybody will have unique signature. So that kind of thing, everything will have their unique signature. So this is called a data cube actually. So this data cube means, like x-axis, y-axis you have, and z-axis have the spectrum. So this RGB and moreover, like say 1 meter by 1 millimeter, like say 1 nanometer also you are resolving. So you are getting some 1,000 bands or something, that you are getting it as this. Because say red is some uh, like some 100 nanometers wavelength is there in red. So but if you further segregate it to 1 nanometer, then you are getting uh, this higher number of bands, and this can be formed as a data cube which can be analyzed. So for analysis of this image will be very high, very big image. One image will be say more than a GB. So how will you cater it? So there comes the expertise of this servers, computer science people. There comes this expertise. So how will you process this image? How will you display this image? How will you store this image? So this is one thing. This what I was telling, spectral signature. You can see this y-axis is percentage reflectance. Reflectance means reflected intensity divided by the incident intensity. That's it. No, not a tough thing. So in the this wavelength region you are able to see. X-axis is your wavelength, 400 to this 800 or 900 we have done visible region. This snow ice, it will have very high. Why high? Now if I take RGB, all are high. So all high means white kind of things you are seeing. That's why snow ice you are seeing white. Okay, so this is the thing. Then this different vegetation have green higher and all these things, dry soil, wet soil, different water, clean water, turbid water, everything will have its own thing. This is comes under remote sensing. So from the signatures you can find whatever like wealth of information you can find from this data. So next I will come to communication satellite. So communication satellite, as it started, like say you want to broadcast from say in Russia something is happening, or Europe something is happening. You want to see it live here. How will you see generally? So like anybody will can volunteer how you see that broadcast. Uh, what are the other ways you can see, or how you are seeing now? Like my presentation, how you are seeing now? Anybody? TV, social media is fine. Somebody answered, but TV, like how is the signal going from here to here? That physical data has to go, no? How it is going?
The antennas,
Okay, antennas is fine, but antenna, like generally from my home there is no antenna to your place. Like it is not communicating directly. So I will tell. From my system, my computer, I am connected to Wi-Fi or some router at my home. So that router, it is taking the data. So I am uploading that data there. So it is taking to some switches there, and then to the telephone exchange, or that whoever is my internet service provider, their exchange. From there, they are sending it to a say bulk. Some fiber optic cable. So from here to, like say I am in Hyderabad now, so from Hyderabad to your place, like say you are in Pune, so that Pune it is sending. From that Pune it is again going scattering again, like based on the signals it will be encoded where the signal has to travel. Like now it is IP basically. So each one of your IPs, it is going slowly. So it is traveling uh, like this, because you have a network from here to Pune. But if I have to transfer a data from here to say uh, uh, Europe, we don't have a direct connection. So now slowly we are having this cables. They are laying under the seabed cables are there. If someone is interested, they can see. So this global network they are doing. But some places, if there is no direct connection, it has to be a direct connection between the places for you to connect. Otherwise, how will you do? So uh, their satellite plays an important role. Say I'm calling you. Okay. This internet I am not telling, because internet there it's a huge bandwidth, and you are generally people are trying now to get into satellite. But but now say I am calling you. So what it will happen, that call will go to this telephone exchange near to me. From telephone exchange it will transmit to satellite. Okay, and that satellite, from that satellite it will go to that nearby telephone exchange to your house, and then from that telephone exchange that signal will come. So why here satellite is needed is like if you don't have this direct line between the places, you can't transmit a data. So their satellite plays an important role. So you are seeing live matches that is happening in say US, or that is happening in Europe, or wherever it is. Now you are seeing that is based on this based on the satellite only. They are transmitting the signal to the satellite, and satellite is retransmitting it to the place near to our house, and then from there we are getting. So that's how I, in the initial slide I have told, geostationary satellite is needed, because that same satellite, as the image shows, that should be visible from the antenna at Europe, and it should be visible from the antenna here. Okay, now many more complications can comes, like satellite to like, say one satellite is viewing India, not this say US, then how will you transmit? So uh, now hopping can be made, like one satellite can transmit from like can take the data from US and dump it to say Europe, like whichever nearby, then another satellite from Europe to India, that can dump. So like this transmission can happen. So those kind of satellites are called communication satellites. In communication satellite, you have a receiving antenna, you have a transmitting antenna, and in between you have a repeater means it will be doing some filtering to the signal. Not no, they will not change the signal, they will retransmit it with some new power. So that is called transponder. Okay, that's why those payloads are called transponder. So those are communication satellites, and after this, it is a huge uh, topic only, because like you are receiving a communication not only from one antenna, you will receive from several antennas. How will you distinguish? So those have to be multiplexed, then demultiplexed, and then sent respectively uh, to like the ground stations. So it's a huge job. So uh, generally when like say some scientific team has gone to Antarctica, how they will transmit with us, or to uh, the main like say India or Europe, or wherever the station is. So they will lease one this geostationary satellite that has visibility over Antarctica and say Africa, or like that has visibility of both the regions. So those transponders are they can transmit. So this Tata Sky and everything DTH service you are getting, those are from these satellites only. These geostationary satellites. These companies are leasing these transponders from the satellite manufacturer, and then providing that services. Okay, so uh, this is communication, and after this another topic comes is navigation satellites. So what is navigation satellites? Uh, Navigation means, uh, can anybody define what is navigation? Let's see what you know. Any random answer also fine.
So it's like finding a path or locating something or someone.
Yeah, correct. Finding a path. So if you are finding a path for yourself, first you have to know your location. Okay. First you need to know your location, then you will be able to see, like you found a path, but how will you go you to know? You have to know your location only. So that your location, how will you get? Generally, you all know, because this GPS signals you are getting, how you are getting this GPS signal, how it is able to locate you. So generally, that method is called that algorithm is called trilateration. So that I can explain a little bit, but not in detail, because it's more complex also. So see, this is say this blue and green, two satellites are there. Okay, uh, now these two satellites have two intersecting points. Okay, so say your phone is receiving signals from two satellites, then you can be at any of the point. Okay, any of the point in between that in between which is overlapping part, like intersection of these two. So you can't locate. So if you have a third satellite, that is this orange one, and then the intersection of all these three will be this single point only. So you will need at least three satellites to locate you. This method, this is trilateration method. You can get more details of it. Now comes more things, like say you got the information of your phone with three satellites, you are getting x and y where you are. Now to get the height, you will need the third satellite. That is that red one it is showing, like fourth satellite. So x, y, z if you want, like altitude also you need, no? Like in Google Maps or wherever you are at what altitude they will show. So uh, those for that four satellites. Now more complexity will come. Uh, how much time you will require to go from here to here? That time how will you get? So for time, some fifth satellite is also needed. So uh, like this. Like 5 6 satellites like are needed to know your precise positions. The more the satellites, the accuracy will be further more, because it will be intersection of those many circles that point. So so the thing is, like in GPS is a program by US Defense. It has started many years back. It is every satellite is in MEO only, and those GPS is very like anytime you will get 5 to 6 satellites visible on your phone. So that's how they are global positioning they are giving. That's why it's global positioning system. So this is navigation satellite, and uh, so next is, like as I told, as like this Aditya and like whatever missions we are doing. So generally from ISRO we have all the satellites, like remote sensing satellites also there. We have navigation satellites also, like recently launched, if you are aware. Then you have this communication satellites also, like that is giving this television broadcast and all those things. And now we have the science missions also. In science missions we have basics. I am covering here the basics. I am not going in gone into detail, because this remote sensing, as I told, it can be visible infrared or this microwave. Now this x-ray also you are seeing, so that's why this exposat has came. uh, Now all these satellites are in orbit around the earth only. You are observing earth only, so that's why this earth observation satellites are there. Now you want to observe this moon also, so you have sent Chandrayaan. So that is all. The Chandrayaan, everybody knows, you have landed successfully, but that Chandrayaan 2 has a orbiter also. Like one has impact probe, 2 has orbiter. So that exact details you go through, you will get, it's openly available in internet. So you will have orbiter also, so you are getting full image of the moon also. So you have this Mangalian mission also we had. So that is the remote sensing of Mars. So Mars also we are evolving one orbiter. That orbiter will give image of Mars and all those things. Now you have one this satellite observing Sun also, that is this Aditya, and it's in some special orbit, as I told. Why that orbit is needed, that also I told. So and the instrument there is more complex instruments are there, like not only camera. Like this exposat, if I go in detail, it will take a long time to explain, because uh, x-ray, that detection of x-ray is little bit different from your uh, general camera or something. So one is x-ray, then one that x-ray polarimeter is also there. So polarimetry is, like polarimetry is there in micro satellites also. Polarimetry is there in this optical satellites also, but optical generally we won't use much polarimetry, because your source is your sun only. So that polarization control is in the hand of sun only, not us. We can filter it and see different polarizations, but not of much use. It will be of little bit use only, but not that much. But in microwave, you are sending your signal, as I told. It's an active sensor, so you are pumping some signals, and you are getting the reflection of the signal. So what polarization you can send, that will be in your hand only. So polarization, I am not going in much detail. I am again repeating, because it's a vast topic. Because for that you have to know this like electromagnetic field, how it is moving. So electromagnetic field, everybody would have studied in your plus 2 or first year. You might be studying that electromagnetic field, like your light is neither a EM wave nor a particle wave. Those things you have gone through in 11, 12 also. But this EM wave, what is EM wave? Electromagnetic. Actually, there is one electric field and one magnetic field that will move in, like, that will change in harmony to generate this wave. So generally, EM wave is like that. So that movement of that electric field, how that electric field is moving, defines your polarization actually. So it's actually the locus of the electric field vector. So if you go detail, it will be little difficult. So that those things also had to be considered while sensing, because different kind of polarization if you send, you will get different kind of signal. So, and those signals can signify the details of the object very precisely. You can get wealth of information of the object you are detecting. So that's how these things are there. Now this recent mission is also coming, that NISAR, if you all have heard. So that is actually joint operation of NASA and ISRO. So that has a this microwave sensor only. Uh, uh, so that will be operating in L band and S band. That L band and S band is some frequency bands that if you go through you will get. So those, and it will have polarimetric informations also. So all these informations can be used to generate this images. Not only this Google, that's why I told this is not just Google Maps. You are not getting that photo of the streets and you are just navigating. That is not just that. It is more to that. So this is what I can share. There is more thing also I can share, but in this time I could plan this much only. Like if you have some questions, you are welcome now. So it's open to you, and thank you very much.
Hello, sir.
Yeah, hi.
Hello, sir. Sarvesh Dhaibar here. Sir, I wanted to ask that after engineering, if I want to pursue career in astronomy, so how can I do it?
That you have many options, like you can do your masters in astronomy or some physics related thing, and then finally you can get. So what is your like basic questions, like basic question like what you wanted to do? You want that specific college information or something, or
Sir, like in research field, observational astronomy.
okay, that actually the thing is you need to study that is the most thing. So BTech, after BTech there is a whole lot of opportunities there for you. You can apply for masters, or you can apply for, because generally if you go for job after BTech you won't be able to do in astronomy.
Yes, sir.
that
Sir, I want to do masters in astronomy only. So which stream is more right?
you can do in physics only, that also is possible. So you find your interest first, and then
Okay.
based on that you find out which course is more aligned to your this field of interest,
Oh.
and then you can pursue that.
Okay. Thank you, sir.
Any other question?
Does anyone have any question? Well, sir, thank you so much for your time. Session was very much interesting. So now I would like to call Harshvardhan for giving vote of thanks.
Good evening, everyone. A very big thank you to Mr. Supantha Sen for gracing us with his knowledge and inspiring us with a huge humongous amount of the knowledge which he has. As we all know, he is currently working as a scientist at ISRO. Let's express a great gratitude towards him, as he has taken out a time for all of us so that we could gain some knowledge from his experience which he is working with ISRO. Also, we could gain a lot of insights about ISRO's greatest projects till date. So, as we conclude this event, May the sparks of curiosity be ignited in our minds. Thank you and have a stellar day. Thank you, everyone.
Thank you very much.